Hello everyone. Today we learn about convergence of geometric series. Geometric series. The positive term geometric series 1 plus r square plus r cube up to infinity converges for r less than 1 and diverges to plus infinity for r is greater than or equal to 1. Case 1, 0 less than or equal to r less than 1. Let Sn be the sequence of its partial sums, so that Sn is equal to 1 plus r square plus r cube plus dot up to r to the power n minus 1 is equal to 1 minus r to the power n by 1 minus r equal to 1 by 1 minus r to the power n by 1 minus r less than or equal to 1 by 1 minus r for all n. Since r is less than 1, so r to the power n tends to 0. Therefore, the sequence Sn is bounded above and hence the series converges. Therefore, case 2, when r is equal to 1, then Sn is equal to 1 plus 1 plus 1 up to nth terms is equal to n, so that Sn is not bounded above and hence diverges to plus infinity. Case 3, when r is greater than 1, every term of the sequence Sn after the first is greater than 1, so that Sn is greater than 1 for all n. Therefore, the sequence Sn is not bounded above and consequently the given series diverges to plus infinity. Hence, the given series converges if r less than 1 and diverges if r is greater than or equal to 1. Theorem. A positive term series sigma 1 by n raised to the power p is convergent if and only if p is greater than 1. Proof. Let Sn denote the sum of the first n terms of the given series. Case 1. When p is greater than 1, then 1 by 1 raised to the power p is equal to 1. 1 by 2 raised to the power p plus 1 by 3 raised to the power p is less than 2 by 2 raised to the power p is equal to 1 by 2 raised to the power p minus 1. Because since p is greater than 1, 1 by 3 raised to the power p is less than 1 by 2 raised to the power p. Therefore, 1 by 2 raised to the power p plus 1 by 2 raised to the power p is equal to 2 by 2 raised to the power p is equal to 1 by 2 raised to the power p minus 1. In similar way, we can show that 1 by 4 to the power p plus 1 by 5 to the power p plus 1 by 6 to the power p plus 1 by 7 raised to the power p is less than 4 by 4 raised to the power p is equal to 1 by 4 raised to the power p minus 1, which is equal to 1 by 2 raised to the power 2 into p minus 1 is equal to 1 by 2 raised to the power p minus 1 whole square. 1 by 8 raised to the power p plus 1 by 9 raised to the power p up to 1 by 15 raised to the power p is less than 8 by 8 raised to the power p is equal to 1 by 8 raised to the power p minus 1, which is equal to 1 by 2 raised to the power p minus 1 whole cube. In this way you can show that 1 by twice raised to the power n whole raised to the power p plus 1 by 2 raised to the power n plus 1 plus p plus up to 1 by 2 raised to the power n plus 1 minus 1 whole raised to the power p is less than twice n raised to the power n plus 1 minus 2 raised to the power n by 2 raised to the power n whole raised to the power p is equal to 1 by twice raised to the power n raised to the power p minus 1 is equal to 1 by twice raised to the power p minus 1 whole raised to the power n. Adding them we have s 2 raised to the power n plus 1 minus 1 is less than 1 plus 1 by 2 raised to the power p minus 1 plus 1 by 2 raised to the power p minus 1 whole square plus up to 1 by 2 raised to the power p minus 1 whole raised to the power n. This is a geometric series with common ratio 1 by 2 raised to the power p minus 1. So this quantity is equal to 1 minus 1 by 2 raised to the power p minus 1 whole raised to the power n plus 1 by 1 by 1 by 2 raised to the power p minus 1. After simplification we get s 2 raised to the power n plus 1 minus 1 is less than 2 raised to the power p minus 1 by 2 raised to the power p minus 1 minus 1 for all n. We know that when n is any positive integer, then 2 raised to the power n plus 1 minus 1 is greater than 2 raised to the power n, which is greater than n. Therefore, Sn is less than s raised to the power twice n less than s 2 raised to the power n plus 1 minus 1, which is less than 2 raised to the power p 2 raised to the power p by 2 raised to the power p minus 1 minus 1. Since for a given p 2 raised to the power p minus 1 by 2 raised to the power p minus 1 is a fixed number, therefore the sequence Sn of partial sums of the given positive term series is bounded above, and hence the series converges for p is greater than 1. Case 2. When p is less than or equal to 1, we know that if n is any positive integer and p less than or equal to 1, then n raised to the power p less than or equal to n implies that 1 by n raised to the power p is greater than or equal to 1 by n. Therefore, 1 plus 2 raised to the power p is greater than or equal to 1 plus half, which is greater than half. 1 by 3 raised to the power p plus 1 by 4 raised to the power p is greater than or equal to 1 by 3 plus 1 by 4, which is greater than 2 by 4 is equal to half. 1 by 5 raised to the power p up to plus 1 by 8 raised to the power p is greater than or equal to 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8 is greater than 4 by 8 is equal to half. 1 by 9 raised to the power p plus 1 by 10 raised to the power p up to 1 by 16 raised to the power p is greater than or equal to 1 by 9 plus 1 by 10 up to 1 by 16, which is greater than 8 by 16 is equal to half. In this way we can show that 1 by 2 raised to the power m minus 1 plus 1 whole raised to the power p plus 1 by 2 raised to the power m minus 1 plus 1 whole raised to the power p plus up to 1 by 2 raised to the power m raised to the power p is greater than or equal to 1 by 2 raised to the power m minus 1 plus 1 plus 1 by 2 raised to the power m minus 1 plus 2 plus dot plus 1 by 2 raised to the power m is greater than 2 raised to the power m minus 2 raised to the power m minus 1 by 2 raised to the power m is equal to half. Adding these terms, we have s 2 raised to the power m is greater than m by 2. We shall now show that Sn is not bounded above. If G be any number, however large, then there exists m belongs to n such that m by 2 is greater than G. Let n is greater than 2 raised to the power m. So, Sn is greater than S2 raised to the power m is greater than G. Thus, the sequence Sn of partial sums of the given series is not bounded above, and hence the series diverges for p less than or equal to 1. Thus, the given series sigma 1 by n raised to the power p converges if and only if p is greater than 1. This proves the theorem. Some important limits. 1. Limit n tends to infinity n raised to the power 1 by n is equal to 1. 2. Limit n tends to infinity log n by n is equal to 0. 3. Limit n tends to infinity 1 plus x by n whole raised to the power n is equal to e raised to the power x. 4. Limit n tends to infinity 1 plus x by n whole raised to the power n plus p is equal to e raised to the power x. Limit n tends to infinity 1 plus x by n whole raised to the power p is equal to 1, where p is a finite number. Limit n tends to infinity c0 n raised to the power p plus c1 n raised to the power p minus 1 plus c2 n raised to the power p minus 2 plus plus cp minus 1 n plus cp by d0 n raised to the power q plus d1 n raised to the power q minus 1 plus d2 n raised to the power q minus 2 plus up to dq minus 1 n plus dp is equal to c0 by d0 if p is equal to q is equal to 0 if q is greater than p, infinite if q is less than p, and c0 greater than 0, d0 greater than 0, where ci's are constants and di's are also constants. Thank you very much for watching this video. Please subscribe my channel. Please like, share and comment on this video. Please press the bell icon to get notifications.